We're now going to take the ideas we just saw and look at different instances of different complexity classes. So what are those ideas? Given an algorithm, we want to count what are the number of basic steps it's going to need. We want to count those as a function of the size of the problem. And we're only going to worry about the case when the size of that problem tends to get large. What is the asymptotic behavior as that happens? We're going to see in this segment a set of examples of different complexity classes. We're going to see constant time algorithms referred to as O of 1. We're going to see logarithmic. We're going to see linear. We're going to see log linear, or n times log n. We're going to see polynomial, and we're going to see exponential algorithms. Let me say a word about those last two because they are actually different and sometimes people get confused by them. A polynomial time algorithm is something whose number of steps asymptotically is n, where n is the size of the problem, to some constant. So a quadratic algorithm is n squared. Cubic algorithm is n cubed. An exponential algorithm is one where the number of basic steps asymptotically is described by some constant to n, the size of the problem. So that could be 2 to the n. And keep in mind that n squared grows in a very different manner than 2 to the n as we change n. And in fact, this sequence is really listed in roughly the order of increasing complexity. Each one of these classes describes a slightly more complex kind of algorithm. And as a consequence, we tend to want to be as high up in this chain as we can. If I have two algorithms that solve the same problem, one of them is quadratic, the other one is linear, I want the linear one because it's almost certainly going to be more efficient. If I got an algorithm that is log linear, n log n, and another one that is just logarithmic, I want the log one because it's always going to be better. Finally, we tend to be a little sloppy in this subject in terms of how we use these terms. Really what we're talking about here are upper bounds on the complexity of the algorithm, on the number of steps. In many cases, it's an actual tight bound. It's both an upper and lower bound. But if we're not certain about an algorithm, we may end up saying, for example, that it's exponential because the best analysis we can do says that the running time may involve an exponential number of steps. It may be possible to show that it's less than that, but if we can't actually do it, we're going to use the upper bound to capture the class. With that, let's start looking at some examples. So the first class is constant complexity. That says the complexity is independent of the size of the input. This is great. And unfortunately, there aren't very many interesting algorithms in this class. It says, literally, that the number of steps doesn't depend on the size of the algorithm. And while pieces of code may satisfy that, it's not common for an entire algorithm to have that property. If you got one, though, still great. And note, by the way, that even in this case, you can have loops or recursive calls. It's just that the number of iterations through the loop or the number of recursive calls is independent of the size of the input. All right, let's move on, though, to more interesting ones. Logarithmic algorithms. Here, the complexity of the algorithm, the number of steps, grows as the log of the size of one of its inputs. And you've actually seen a great example of this. Bisection search. Remember when we were looking for square roots, we said start between 0 and x, take the midpoint. If that's close enough, we're done. If not, depending on the size, either we're going to look only in the bottom range or in the top range. Again, we take the input, the midpoint. And either we look at the bottom range or the top range. At each step, we're cutting down the set of possibilities of which we need to look by a factor of 2. And that cutting down a problem in half constantly is a great indication of, in fact, a logarithmic algorithm. So bisection search is a great example. You can do the same idea, by the way, on a list. If I have a list of elements that are in order, and I want to decide if an element's in that list, use the same idea. Look at the midpoint. If I happen to get lucky, I'm done. If not, based on the size, either I'll just look at the bottom half of the list or the top half of the list. So that kind of property is indicative of a logarithmic search, a logarithmic algorithm. Now, let me show you an example of a piece of code doing this, just to show you how we would reason about it to decide whether something's logarithmic. This is a little piece of code to convert an integer into a string. Don't worry about the fact Python will do this for you automatically. Let's just see how the algorithm shows logarithmic complexity. I'm going to set up an internal variable called digits. It's just the string of all the digits. And then given I, if it's 0, I'm done. If not, what am I going to do? I'm going to set up a little variable result that's initially an empty string. And then I'm going to take that integer I. And the first thing I'm going to do is I'm going to take the remainder, which basically pulls off the bottom digit. I'm going to index into digits to find the corresponding string representation. And then I'm just going to add that to the front of result, putting it in the right spot on the thing that I'm accumulating. And having done that, I'm going to divide I by 10, which throws away the bottom digit, shifts everything to the left, or to the right rather, and I keep doing that. Now, if I were to count steps here, what really matters is that loop. And in fact, let's look at that. I only have to look at the loop because there are no function calls here. And within the loop, how many steps do I have? Well, I've got the remainder, that's 1. I've got the add, that's 2. I've got the lookup, that's 3. I've got the assignment, that's 4. I've got the division, which is 5, and the assignment, which is 6. So there are 6 steps within the loop. But it doesn't depend on the size of I. It's always the same thing, 6 steps within the loop. So really what matters is how many times do I go through the loop? And for that, I have to think about, so what is changing? And what's changing is the iteration variable, or the loop variable I. And at each stage through the loop, it gets divided by 10. So how many times can I divide I by 10 before I get down to a single digit case? And the answer is a logarithmic time. So this is order log n. Now, let's be careful here. You might say, well, wait a minute. Why doesn't this depend on the size of the integer that I pass in there? And it depends not on the size, but on the number of digits. Another way of saying it is, if I have some number of steps to solve a problem with one version of I, and I take 10 times I, I'm only going to go through the loop one more time. It's the number of digits, not the size of the problem. And that's why it's logarithmic in the size of I, because that log gives me the number of digits. How about linear algorithms? Well, searching a list where I just walk through it in order is a great example of a linear time algorithm. In the worst case, I've got to look at every element of the list, so it's linear in the size of the problem. Here's another example of a linear algorithm, and I want to use this to look at how we measure it. Suppose I've got a string that's assumed to be composed of decimal digits. I want to add up the characters of the string to get a number out. A trivial little thing to do, but let's look at what the code might look like. I'm going to start off with some initial internal variable called val, and for each character in the string, I'm going to convert it into an integer and add it into what I've got in val in order to return that overall value. I don't care about the computation. What I care about is the complexity. And the complexity is pretty straightforward. I have to go through each element in the string once. So this is linear in the length of the string. Within the loop, it's a constant number of things to do. So all I care about is how many times do I go through the loop. And that is linear in the size of the problem. So far we've seen examples where we're just looking at things that have loops. And we're worrying about how many times does it go through the loop. We can also have a complexity that depends on the number of recursive calls. And our good friend factorial is a great example. There's the code for factorial. You've seen it before. If I think about the complexity of this, I could say, well, within the actual code itself, there's only a constant number of things to do. I'm doing a test. If the test is true, I'm just returning something. Otherwise, I'm doing a multiplication and a recursive call. But for the body of the procedure itself, it's a constant number of things. So what matters here is how many times do I call factorial? And we can see that on each recursive call, we're reducing n by 1. So I've got to do fact of n, then fact of n minus 1, then fact of n minus 2. And you can see that I'm going to call factorial n times. Within each call, complexity is constant. So therefore, this is linear in the size of the problem because there's a linear number of recursive calls. Algorithms with this kind of template are typically linear. And that's a handy thing to know. What about log linear? Well, a lot of practical algorithms fall into this category. They're n times the logarithm of n. In fact, an example we're going to see later on is one of the most commonly used log linear algorithms, which is an algorithm called merge sort, which is a way of sorting a list to get it into increasing or decreasing order. I just want to highlight that we have algorithms of this sort. We're going to come back to merge sort later on to see how we can do reasoning to find these kinds of examples. So let's move on to polynomial. Polynomial complexity says I've got an algorithm that grows as n to some power. And most common polynomial algorithms are in fact quadratic. They grow as n squared, or some parameter, some size parameter squared. And these commonly occur when we have nested loops or when we have particular kinds of recursive function calls. So let's look at an example. And this is probably a good example of a very common kind of quadratic complexity. This is a little algorithm that's going to decide whether, given two lists, one of them is a subset of the other. And that says, is every element of L1 in L2? The code to do this we can describe pretty quickly. We're going to loop over every element in L1. We're going to set up each time through the loop to say a variable match is equal to false. And what am I going to do? I'm going to loop over every element in L2, or almost every element in L2, looking to see if I find one that's equal to E1. If I find something that's equal, I set the flag to true, and I break. And what that break does is it throws us out of this loop, this interior loop, which means I can then skip down to basically this step here. And if in fact matched is false, I return false. But if it's true, then I simply skip back around. Okay, and that then says I'm going to basically run through this loop until either I go all the way through, in which case matched is false because I didn't find an instance of it, or I do find an instance and I break out of it and I set a value that returns. Right, I'm going to do that over all versions of this outer loop, E1. So let's look at an example to see how we'd measure the complexity here. All right, the outer loop is executed the length of L1 times. So however long L1 is, I'm going to do that outer loop that many times. Each iteration is going to execute the inner loop up to the length of L2 times. If I have to go all the way through L2, it's length of L2. If I find something earlier, I'll break out of it. So in the worst case, this has a complexity that's the product of length of L1 times length of L2. Now, that depends on L1 and L2. What is the actual worst case? Well, the worst case is when they're both of the same size. L1 can't be bigger than L2 or it wouldn't be a subset. When they're of the same size, but none of the elements of L1 are in L2, then I'm going to run through this loop the full number of times. I'm going to run through it L2 times. In that case, the complexity is quadratic. It's the length of the length of L1 squared. It's quadratic in that size. Let's look at another example. Okay, another example involving two lists, and I want to find the intersection of those two lists. And here I'm going to show how having multiple loops, we're going to focus in on the one with the worst complexity. The idea here is I want to take two lists, L1 and L2. I'm going to set up an initial temporary list, and then I'm going to loop over everything in L1. And for every element of L2, I'm going to look to see, is it equal to the thing I'm looking for in L1? And if it is, I'm going to add it into temp. Now, because L2 might have multiple instances of something, I'm going to keep going. So even if I find an instance of E1 in L2, I'm going to go all the way through L2 and gather each of those instances together. I'm going to do that over all possible versions of E1. And when I'm done, I need to now strip away the duplicates. So I'm going to set up another temporary variable, res. And then I'm going to loop over that list I just built, temp, and basically say if E is not in res, then I'm going to add it in. But if I've already got a version of it there, I'm simply going to ignore it and keep going so that I ultimately return a list of unique elements that are those that appear in both lists. Again, what's the complexity here? Well, to see this, we can note that this first nested loop up here is very similar to what we saw before. It's going to take the product of the length of L1 and the length of L2 number of steps. And in fact, it's going to do exactly that because I go through L2 in full each time around. What about this loop? There's a second loop there. I have to think about that. Well, that second loop takes at most the length of L1 number of steps because I'm simply going through that list once. So I've now got two terms. I've got a quadratic term and I've got a linear term. And of course, we know that the quadratic term really dominates here. It's the big one. It's the one that really matters. So I can ignore the second term and basically say that this is of order length of L1 times length of L2. So it's quadratic. The point of this is I need to look at the loops. If I have different loops or multiple loops within a piece of code, I need to find the one that has the higher complexity. And that will tend to be the nested one, as it was right there. Okay, what about exponential algorithms? What characterizes an exponential algorithm? And an exponential algorithm, by the way, is usually a very expensive algorithm. Well, it's typically a case when we've got recursive functions where there's more than one recursive call for each step of the problem. We saw an example earlier. Towers Hanoi has two recursive calls. I moved a smaller stack once, moved the bottom case, and then moved the smaller stack again. So I had two recursive calls for each size of the problem. And that is characteristic of an exponential problem. Well, unfortunately, many important problems are inherently exponential. And that's really unfortunate because the cost can be very high. And one of the things we want to see is that's going to lead us to consider finding approximate solutions in more efficient time rather than trying to do something that deals with finding the exact solution. Nonetheless, let's do one last example here. Let's look at an example of something that is exponential in complexity and look at how we would actually measure it. So this is an example where I've got a list of elements, for example, it might be a list of numbers, and I want to generate another list of all of the subsets of that list. So if the list is 1 and 2, I'd like a new list as output that has the empty list, the list of 1, the list of 2, and the list of 1 and 2. So all the different possible subsets or combinations of elements out of that list. Again, I'm not as worried about it, but I want to see how the complexity grows here. So here's what the code does. I'm going to set up a place to store my answer. If there's nothing in the list, if the list is of length 0, then I want to return a list that is just a list of the empty list. So there's this funky looking thing right here with 2 square brackets. So it is a list whose only element is the empty list, because that's the only possible subset of a list of length 0. Otherwise, how am I going to solve this? Well, I'm going to use that recursive idea. I'm going to first say, let's take everything in the list but the last element and get all the possible subsets of that. I'm going to call that smaller, right here. I'm going to get a list of just the last element, right there, which is extra. And here's what I want to do. I want to take all of the things in smaller and add that last element to them, because those are all subsets of the longer list. And then I want to take all of the instances, all of the subsets without the last element, and all of the subsets with the last element and add them together. And I'm done. So there's a little loop where I take everything in the smaller one and I add that last element onto it, and I create those into new. And then finally I create a flattened version, which is all of the versions without the last element, all of the versions with the last element, and I'm done. You can go code this up and try to see that it does the right thing. What I'm really interested in is the complexity. So to measure that, I'm going to assume that append is actually constant time. In fact, it is, given the implementation inside of Python. But since it's not a basic element, I need to make that assumption. And now what do I want to look at? What's the time? Well, the amount of time it's going to take here is basically going to be the amount of time it takes to solve this problem, the smaller size problem, plus the amount of time it's needed to make a copy of all of the elements of the smaller problem right there. Okay? So how can I get at that? Well, it's important to think about the size of that smaller problem. And in particular, we know that for a set of size k, there are 2 to the k cases. There are 2 to the k different possible subsets inside of there. So if I want to solve a problem of size n, I'm going to need to solve a problem of size n minus 1, and there are 2 to the n possible problems, solutions there. And then in the problem of size n minus 2, there are going to be 2 to the n minus 1, and so on, all the way down to 2 to the 0. Now, we can actually solve this, but a little bit of math actually tells me that that sum, 2 to the 0 plus 2 to the 1 plus all the way up to 2 to the n minus 1, is 2 to the n. And so the math tells us that this is a problem of size 2 to the n. This is important because it looks like there's just one recursive call at each step, and there is. But it's on a problem whose size is growing exponentially. And that therefore, when I come down here and I want to walk through that list, basically adding all of them in, that loop there has a size that's order 2 to the n for whatever the length of the list L is. And as a consequence, this is an exponential sized algorithm. Okay, so what does that give us? It says we've now seen a sequence of different instances of classes of algorithms. We see characteristics or templates of each one of them, and we've seen that as we go down this list, they get worse and worse. As we go through the rest of the course, we're going to see examples of this complexity, but those templates already give you a way of getting a sense of what is the complexity of a particular solution.